Thanks everyone for joining us and of course for your time. We are excited to bring you a burning topic here, and I know you all want to know everything about RF interference. So Don is ready for you, and we've got some good questions. We'll call them out at the end, but please do, if you have questions ongoing, you can throw them in the questions and answers, and I'll be happy to field them as best as I can. And if we miss any, we'll address them at the end. So without further ado, Mr. Boomer, take it away.
Yeah. So we're going to talk about radio frequency interference, RFI, as it pertains to wireless mics. It's a much bigger subject, but nobody, I guess, is sending satellites to Mars, so we don't have to worry about that. We'll just keep it the discussion to wireless mics. So, what is radio frequency interference? Well, it's everything unintended, everything other than your single, if we're talking about one mic, your single frequency. Some of these are man-made, some of these are intentionally man-made. Let's move on to that. Yeah, it's like everything. Some of them are just natural conditions, lightning, things like that. And then basically pretty much anything with electricity going through it causes some amount of RF interference. For you quantum physics fans, actually, according to what they call Planck, anything with a temperature above 0 Kelvin generates what they call black RF. Yeah, forget I said that. We don't need to know that. So here's some things. I'll let you kind of look through the list here. Like I said, the natural radiators, lightning, solar flares, cosmic microwave background for you Big Bang theory enthusiasts. Radio waves that were caused when the universe was formed. They're floating around everywhere. And then there's unintentional radiators, mostly things to do with electricity, switching electricity. Every time you flip a power switch on and off, it generates at least a little RF. Things like X-ray machines, don't have too many of those on stages. And then other radios. Every radio of every frequency is generating some garbage that sits at our noise floor, right? The closer they are in frequency to the frequency you're trying to use, and or the higher power that they are, the more they interfere. But every other radio, computer, the computer like Wi-Fi and Bluetooth and all those kind of things, cordless phones, video cameras actually have radio transmitters in them, a lot of them so you don't have to use cable to hook it up. And all that stuff adds up. And so here's where we're at. It's kind of a Where's Waldo thing. There's all this stuff out in the world, and we're just trying to get our microphone back to our receiver, right? So there's no way to escape all this stuff. We just have to kind of have more power than it does. So if we look at if we look at this, a little scan here, the noise, the accumulative RF interference is that sort of blue bunch of garbage down there at the bottom that's below -90. And so, you kind of look at that. If you kind of draw a line through the middle of that squiggly thing, that would be the average level. We're probably more concerned with the peak levels because they can jump in and cause little dropouts. So kind of like I always say, this is our primary goal, to get the signal of our microphone at least 20 dB hotter than whatever the noise floor is there. Actually, that yellow arrow shouldn't go quite down as far as it does. It should be to the top of the noise. So once we've got a signal that's much stronger than all the interference, the radio locks to that. It's the only signal it demodulates. It stops looking at everything else. And so as long as we can keep our signal above, more than 20 dB above that noise floor, we're likely to never have a dropout, right? So this is our goal. So and what we'd like to have, if you have a way to scan, if you have a scanner, you can do it with some of the newer digital radios, kind of, but they only look at the frequencies they can tune to. So you're missing stuff that's out of band, but it's better than nothing. You can kind of get an idea of your noise floor. Once we have a number for your noise floor, then we can calculate all this stuff out. If we're guessing, I mean, pretty much everybody tells me, well, there's no noise. How do you know? Well, I don't see any. Well, it's invisible. You can't see it. And places you think should be completely empty of noise can be completely full of it, and backwards to that. You really need to be able to measure this anymore. The days of getting good results from guessing are behind us, or almost completely behind us. So measuring, this is the way to know, right? We can guess, and you might get lucky. You probably will get lucky, but you may not always be lucky. So measuring is really the way to do it. Here we go. It's a little more easy to see. So again, once that signal is above the noise floor by about 20 dB, CNR is carrier to noise ratio, or otherwise known as dynamic range. Once you're that far above it, your radio develops something called capture effect, and it locks to that signal, and all the rest of that stuff goes away. It becomes invisible to your radio. Okay, so so now we know what it is, and there's really no escaping it. What can we do to avoid interference from it, bad effects from it? And the answer is not really a whole lot that does, that does tremendous amounts of good, but there's some small things that we can do that, again, if we can just improve this by a dB or two, that gets you above that 20, hopefully, because on a good day you might have 30 or 40, but we need to stay above 20. So let's look at things that we can do that will help us minimize the bad effects of radio frequency interference. So the first thing is directional antennas tend to pick up less noise than omnidirectional antennas. So paddles, circular polarized antennas, anything that has a more limited coverage area, the noise, generally speaking, we consider the noise to be kind of even all over the place, right? It could be a little, it could be a little stronger coming from the north where you are, but we generally kind of, we think of it as even coming from all different places. So, I mean, if you have an X-ray machine in the northwest corner of your building, well, that's where the noise is coming from, but who's got an X-ray machine in there? So simply because a directional antenna is looking at a narrower coverage space, it simply sees less noise, probably half as much noise as a whip antenna or an omni antenna. Now, that doesn't mean you can't use those antennas. Sometimes those are the right thing. But given a choice, I would almost always pick a directional antenna, at least from the start. If I know some other specific reason, but I got to tell you, omnis are the right answer about one time out of 1,000. So all the rest of the time, it's kind of the same way you use microphones, right? You probably use your cardioid microphones, and you probably don't use your omnis very much, although they are exactly the right tool for some things, and the cardioids aren't. So same with this. The more focused your antenna is, the less background noise it's likely to pick up. So that should seem pretty straightforward. The second thing is, when you move your antennas closer to the source, you end up with a stronger signal, right? So again, if we look at, we've got our antenna up and noise is all around, okay? So, but what we're concerned with is signal to noise ratio. That's what we're concerned with. So when you simply get the antenna closer to the transmitter, the signal's stronger. The noise doesn't change. But if you look at this, and it varies with frequency, it varies with a lot of things. So these numbers don't hold every single time. They're just for demonstration. But it's inverse square law. It's just like speakers, right? Every time you double the distance back from your speaker, you cut the power level, you cut the SPL by to a fourth until you get in the reverberant field. So the same way, if you can get your transmitter 25 feet from the antenna, let's say you got a signal of minus 45. If I double that distance from 25 to 50, I lose 6 dB of signal, but the noise stays the same. So my dynamic range is dropping down, and that's what I don't want. And again, if I move it back to 100 feet, I lose another 6 dB. So the difference between having your antenna 100 feet away from your transmitter and 25 feet away from your transmitter is about 12 dB, right? We're looking for 20. We could make it 12 dB better by just moving the antenna closer. That doesn't mean that you can't put your antenna on the back of the hall. Obviously, probably most of you have done that successfully, and it can work. But when you're really tight against that noise floor, like I said, if you've got 30 or 40, you don't care about giving up that extra 12. It's not important because you maintain that 20. But if it's sketchy where you are because of your local circumstances, you can try moving the antenna closer to the transmitters, and that will give you a stronger signal relative to the noise floor. And that's what makes this work or not, because the noise isn't going to change, but the signal strength in your antenna is, right? Another thing that you can do, and this doesn't cost very much more, but this is now a place where you don't want to save a few bucks. You need to get the best you can get. So we want you to use 100% shielded coax. So if you look at the one on the left there, you can see it has both a braid and a foil shield. And so they say 100%. I don't know if that means 100, exactly 100, might be 99.9999999, but it's basically there's no leakage in or out of that cable. So that means it's not going to pick up any of that noise that's in the room, that electromagnetic interference, right? So, again, from other things running next to other cables, being in the back of your rack with all the rest of the stuff that's cooking in there, that's all spitting out a little bit of junk. And so we don't want those cables to pick up any of that if we can avoid it. And so these coax cables, generally for runs under 100 feet, you can use something like our RG8X, which is double shield. Not all RG8X is, so you need to look at the spec sheet if you buy it from somebody else. There's a company called Times Microwave. Their cables are called LMR. So there's LMR 200. It's almost exactly the same wire as RG8X. And then if you need to go over 100 feet, I would recommend Belden 9913F or LMR 400. That's a bigger wire. It's a stiffer wire. It's a much more expensive wire. And it's like you don't have to use it at 105 feet or maybe 120 feet or maybe, again, if we know that noise floor number, we can calculate this, but these are kind of good rules of thumb. So these cables, yeah, they'll cost more, but if you give it away, you'll never get it back, right? So spend $20 extra for your wire because, just spent $800 for your microphone. Why get it? Why make it cheap? Why would you buy a new car with retread tires? Just get new tires, get good cable. And this will help minimize the interference that's getting back to your receiver. The next thing you want to do, so if you remember back to that list of intentional radiators, that's other radios, and they're on a frequency, and that frequency will interact with the frequency for the microphone you've selected. If we're only thinking about one mic, or you've got 8 mics, it'll interfere with all of those. So examples of that, Out of band, like T-Mobile 5G cell phones will mix all the way down to 500 with your mics and create extra sidebands, extra phantom radio stations. You can measure these. They're just garbage. They're just noise, and it's adding to your noise floor. Because if you look at the picture there with the mics, we're only interested in those three mics. But when we put microphones, when we put radio transmitters near other radio transmitters, they interact and they create additional frequencies. So the way you optimize for that is you use a frequency coordination software, such as our wireless system builder, which is just on any page of our website. There's a button that says performance tools. This is really simple. You just tell it where you are and tell it what microphones you got. Just ask you questions. Really simple. You don't have to do any measurements or anything. Just tell it all this stuff. And it's going to give you a pretty good frequency coordination. If you can scan, if you can measure, and then you can dump that into there, it'll give you an even better one. But for most people that don't have complicated systems and difficult situations, if you've got 24 wireless mics, well, you might need to scan. If you've got 6 or 8, the fewer you have, the easier it is for this to work wherever you are. So this program, if you haven't looked at this, when we're all done, just go to rfvenue.com, our webpage. At the top, there's a round button here. It says performance calculator, but it says performance tools on the main page. Click on that. It'll take you right to this. And this is very simple. Your mother can do this. So this is, again, what we're trying to do. Every one of these little things that we can, every little tiny bit of interference that we can get rid of drops that noise floor a little bit and a little bit and a little bit and a little bit. And so we're always dealing with a straw that breaks the camel's back kind of thing, right? So it's not any straw by itself that's the problem. You just have too many straws. So as we're looking at some of these things, every one of these things you do is going to take a straw off the camel's back, improving your odds of staying on the air without, these are fairly inexpensive or free things. It sometimes gets to the point where, no, the only thing you can do is buy $5,000 radios, but we'd like to avoid that if we don't need to. And then the next thing is to lower transmit power. This is for in-ears or wireless microphones. They're all radios, so the same thing happens. So if we look on the left side here, this shows 4 radios, which are the taller green peaks, and the rest of that is the noise floor. And if you look, there's a few little things poking out. They're kind of easier to see on the left-hand side of that. There's a few little frequencies pointing out. Those are intermodulation, and that means you're not going to be able to tune to those frequencies. However, if you turn the power up, this is the same radios in the same place in the same system, but now we've turned the power up to 50 milliwatts. You can see how much bigger the interference gets, right? It grows 3 times as fast as the power level. So using the lowest amount of power that works, right? You can't use less power than you need, but more than you need is going backwards. It's always creating more rise in your noise floor, right? That your noise floor is your interference, right? So however it got there, whether it got there from sunspots, or it got there from other radios, or it got there from, cordless phones or whatever, we need to try to eliminate that. And by lowering the power of any radio that you can, will lower that noise floor somewhat. So it's pretty easy to see here. The next thing you want to do is that antennas themselves interfere with each other when they're close enough together. So we want to keep our antennas 3 wavelengths apart. And the frequencies that we're using in the US, let's say the middle of the 500s, that's roughly 6 feet. Because what happens is When that antenna receives a radio signal, it has a current flowing through it down into the receiver and you get a radio. But when you put a current through a conductor, that antenna is just a piece of plain copper wire, a very precise length, but it's just a piece of wire. And when you put a current through it, you generate magnetism. And that magnetic field will wander over into your next closest antenna. Again, this is an inverse square. It falls off quickly, but by the time you get about 3 wavelengths, roughly a wavelength is between 20. I think it's actually between 19 and I forget 23 inches and something, or 24 and something for 470 to 608. Anyway, keeping your antennas at least 6 feet apart will minimize. They'll make that almost zero. I mean, it's a little better, even a little farther, but now we're barely doing anything. So 6 feet, maybe 10 feet. Anything beyond that is like, there's no benefit to it. So, but keeping them at least 6 feet apart, which means if you've got two little receivers with their whip antennas, you don't want to stack them on top of each other. They need to be 6 feet apart. And unfortunately, the antennas that are on your receiver, you can't move. You can't move those 6 feet apart. So you're going to get that interference, but at least you can keep the one radio from interfering with the other as best you can. And kind of the last thing that we can do is block this out of band interference, right? So a lot of these things, may be the exact frequency you're trying to transmit on. However, most of these things tend to be, very wide. It's a big fog, not a single. Somebody's not squirting you with a hose with water. It's a big fog that you're getting wet from. It's from low to high. And so if we can block a lot of that stuff from getting into our antennas in the first place, then it doesn't accumulate into the noise floor. And so we've talked about this before, but this is where bandpass filters. So essentially, this is our new all-in-one universal. This is the North American version. We also have a pretty much the rest of the world. The rest of the world uses frequencies higher, mostly up to 698. Some go even higher than that, but they're all changing. Eventually, in the next couple of years, nobody's going to use wireless mics above 698 in this band. There are other bands, but so what these do is they basically block everything that's below 470 and everything that's above 608 from getting into your receiver. Now they turn it down rather rapidly. It's not they don't cut it off like with a knife, but it's pretty close. So you can see the before and after, and you can see how much dark green there is at the bottom in the before. That's all the noise floor. And pretty easy to see that the after is going to be a whole lot easier to deal with than the before. So this is these are a great thing. Yeah, now this one's not real inexpensive. This one's going to cost you $700 or $800 for a pair of these. You need a pair of these, and then you put it on your antenna going into your distro, and it will protect all of your microphones after that point. So whether you've got 2 microphones or 200 microphones, it covers them all. So it gets very reasonable if you have a system of 8 mics or 10 or 12 or 24 or 600. It's not terribly expensive after that. So that basically is what I have to say about radio frequency interference. And I think we have some questions there. We still got some time left. So what you got for me?
For sure. So Dan in the questions and answers gave a really great question that comes up a lot. Do you recommend different wiring for digital versus analog systems?
Well, I don't think about it that way. I recommend using the best wiring you can for everything. That's the way I look at it. It does make more of a difference with digital wireless mics than with analog wireless mics, because over time, digital wireless mics are transmitting more energy than analog wireless mics. Not any higher in amplitude, they're just on more. So they're, the fact that you're pushing more down the wire means if that wire is leaking or that wire is bringing in more stuff, that's more of a problem. But I don't, like I said, digital and analog radios are the same thing as far as RF venue, as far as antennas are concerned. Radios are all analog. The digital part of the radio is the modulation scheme. Like you remember AM and FM. Well, now you got AM, FM, and digital. But it's the radio wave, the electromagnetic energy floating through the air is the same for all of them, pretty much. So just use the best cable you can, which is 100% shielded coax, and that's the best you can do.
Excellent. All right. So these are the questions you guys submitted. Here we go. I seem to have worse performance using wireless products inside an all metal building. Is this typical?
Oh yeah. It's you're getting more multipath with more metal, right? You're getting reflections, you're getting echoes. It's like trying to do a PA system in a basketball gym. It's loud, but it's very confused and very echoey. So yes, it's much harder. If you have to do wireless microphones in a metal Quonset hut, that's a tough day. That's much harder than if it isn't that. And really nothing you can do about it.
All right. Explanation of why analog UHF systems can affect digital systems channel count so much.
Well, it's not quite that. It's just that any radio affects any other radio when it gets close to it. So the digital radios, the way it works, it's using kind of a wider thing. You need more space around it, so it may appear. But another analog radio doesn't bother it any more than another digital radio. Another radio bothers it. The fact that it's analog or digital really isn't really part of that. It's just you've just got another radio, and this depends very much exactly on the frequencies. Going back to that intermodulation thing, that's what happens. So when you get them closer together, you get more intermod, be it analog or digital. So it's that happens to the analog waveform, to the analog part of the signal, the actual radio waves. So it really isn't a matter of analog or digital. It's just a matter of more radios too close.
Got it. All right. How to configure the optics for IEMs?
Oh, the most polite way I can say this is, if you have to ask how to do it, you shouldn't be doing it. I suppose if you ask a brain surgeon, how do I do brain surgery? He could tell you, but you don't want to do it if you don't know what you're doing. So basically the problem is that when you use IEMs, the level of signal that you're transmitting is hundreds or 1,000 times stronger than what it is with wireless microphones. And you run past the limits of the system. So if you want to do it, what you have to do is you have to, greatly attenuate the signal going into the optics, let it run through the optics and grab it on the other side and re-amplify it. And when you want to re-amplify, you can't use the little line amps that we sell for wireless mics. You need a specialized, much more powerful, not more powerful, but one that operates at much higher voltages. So that's an expensive proposition. So it's kind of like, you don't really want to do that.
All right. What other products do frequency coordination besides Shure Wireless Workbench?
Well, our wireless system builder. There's also the one that everybody used for forever, the professionals used forever, was called IAS. That's available, but that one, last time I looked, it was about $600 for the program. Audio Technica has a free program. They're all called Wireless System Manager, I think. Sennheiser has a free one. It's easier to use sometimes those because you have to tell it what microphones you're using. Our system has almost all the microphones anybody uses built into it, so it really doesn't care what brand you're using. If you use those other programs, you probably have to enter a bunch of information. It's not difficult, but it's just you got to build into it a library of stuff. So, but they're all worth doing. Ours or somebody else's. Learn whichever one makes the most sense to you and use it, because using it is going to be an enormous help almost always.
Excellent. I will also mention you can do frequency coordination with the RF Explorer Pro as well. I don't know if you said that and I missed it, but
I didn't say that.
all right. Well,
yeah, we have a new spectrum analyzer that we just started selling. That is it's an order of magnitude better than the last ones that we sold. Yeah, there you go. This really does a lot of stuff. Does a lot of almost laboratory grade stuff that's way beyond what you'll need to do to set wireless mics up. But if you're, looking at engineering level stuff, this program really has a lot in it. And you basically, there's a button that's not showing. If he was on the right screen over there on the right hand side in the gray, there'd be a button that says frequency coordination. And so you just, here you go. You tell it what all your mics are,
in the inventory.
Yeah, there you go. Your inventory page. And this is basically what you're going to do with any of these programs. You have to tell it what you've got. You have to tell it what's there, and then it calculates everything. Now, our system builder will work to a level without telling it what's there, without scans. So with the rest of these programs, you have to have a scan to put in it, and that's better because it's more information. The more data you give it, the better report it can make. But it still should get you awfully close if you don't have the ability to scan.
Excellent. All right. So how to calculate frequencies for a ballroom and several breakouts?
Well, that was just it. You need a frequency coordination program. You basically, the frequency coordination, you tell it what mics you have. I have 6 Shure mics. I have 4 Sennheiser mics. I have 3 Audio Technica mics in these blocks. On ours, you just tell it where you are, and it will figure out pretty close what's there working against you. Or you scan. You measure what's there right now, put it back into the program, and it calculates all those things together. But yeah, it doesn't matter. It doesn't matter doesn't matter if it's a ballroom or, anything else. You just, by doing that, you're going to get the best frequencies for that particular spot. And that's what you're trying to do, because the best frequencies for that spot are going to be taller. They're going to be higher in amplitude, and they're above the noise floor. We're trying to hit that 20. So that's what these programs do. They give you the best frequencies, so the most of that gets through without cross interfering with everything else.
Great. So we got 2 questions in the Q&A. What should I expect in terms of RF coordination when encrypting all my transmitters in the same zone?
Well, that's an interesting question. And I don't know everything there is to know about that. So at some point, because the information isn't, it depends how they've done the radio, honestly. At some point, there may be some small benefit to looking at one or the other, but that depends how they've designed the radio. It's still, until it's demodulated, until you unencrypt it, you're still sending the same frequency twice. And so you get the intermod and you get the interference and all that before it gets there. So as far as I know from the design of the microphones that I do know about, which probably isn't everything that's exactly brand new, it's really not going to make much difference. It might be slightly better, but that's what I'd expect, a very small improvement. So it wouldn't be my plan starting out. If I get it and I get a little extra benefit, well, good for me, but I'm going to just pretend there's none because there really can't be very much. So.
All right. So we got one more here. Is there a difference in the amount of RF interference between 500 megahertz and 900 megahertz bands?
It kind of depends how you look at it. I mean, certainly so we're talking about in the US and a lot of other places around the world, but definitely in the US, there's a lot of television stations in the 500s. Those are 500 megawatt transmitters. And if they're 150 miles away from you, they're interfering with you. You won't find those in the 900 band. There isn't anything about the frequency itself that really makes any difference. There's different interferers. If you go back to that list, and we're going to put this will be up on our YouTube channel in a day or so. You can go back and you can look at that list, which is not a complete list, but you get the idea looking at all those different interference types. So some of them live in different parts of the spectrum. And so if there was a particular, like cordless telephones, there's a lot of those in the 900s. And if you're trying to use mics in the 900s, you're going to run into more of that interference. So if there happens to be cordless phones around you, then that's going to be worse, but there may not be any cordless phones around you. So in that case, it isn't going to be worse. It isn't going to be any different. It's just there's really nothing you can generalize about that, I don't think.
Scanning would tell you, right? If you scan,
scanning tells you. So with the exception of like TVs, yeah, if you're 150 miles from a television transmitter, that particular block of frequencies, it's a 6 megahertz block, is pretty much going to be wiped out. You almost never can use that, and there's some laws about that too, but we don't need to go into that. It's just avoid those. And you won't have to avoid those in the 900s because there's no TV in the 900s unless there's amateur radio TV, which can't be very much of that. I wouldn't worry about it.
All right, one more, and I think that's all we got time for, but are there harmonics created in a combiner, such as in the Shure PA821? Is there a way to minimize the effect? If so?
Okay, so there's harmonics created in everything. I mean, everything has at least some tiny amount of harmonic distortion. I suppose it even gets down to wire, probably. I mean, but that's infinitesimally small. So there's always going to be a little distortion in everything. Mostly it's bad in active devices, things with amplifiers, right? So it's worse in an active combiner as opposed to a passive combiner, but that's a whole different story too. So read me the question one more time because I've...
Sure. Go ahead and find it. Are there harmonics created in a combiner, such as in the PA821? Is there a way to minimize the effect, if so?
Well, so the harmonics created in anybody's particular model of anything is the way they've designed that. I don't suspect there's a whole big amount of difference. I don't know how much difference is there in a Chevy and a Ford. They got 4 wheels and a steering wheel, and you drive it to the grocery store. If you look at it on that level, there's no difference. If you look at it on other levels, there's tons of difference. So I don't expect that you're going to get any more particular interference. And it depends exactly what frequencies you're using too. See, so if you tune, 501, 502, 503, you're going to get a different answer than if you tune at 521, 22, and 23. Which one's worse? I don't know. And then if you split the difference, some at 501 and 502 and some at 520, it becomes unique. It's you can't generalize about that too much. So
Great.
yeah, I guess what I'm saying is I'm not particularly worried about that. Yes, there is some level of harmonic distortion generated in pretty much everything that has an amplifier, and kind of the higher you go in frequency, the more detail you have to look into in the electronic design of that piece of gear. But
From my studio days, I know that this stuff crops up in audio gear when you reach the threshold of distortion, and anything else is so low, it's imperceptible to your ear until you do such a thing. So I don't know if it's the same in combiners, but I'd guess it's the same for any analog electronics. But guys, it's been great. Thank you for all the questions. I'm curious to know, I'm going to launch a poll at you guys. Let me know how many webinars you have attended previously. It's always good to know what our audience is and, how many they've been on with us. So go ahead and hit that poll for us.
yeah, we kind of like to know this, so I know how much I'm repeating myself.
Can you see that, the results, Don?
Yeah.
Great.
Yeah, it looks it looks like it's about 25% for every one of the
Almost looks
categories.
like RF meters bouncing around.
Yeah, there we go.
Not
Good.
much interference in this session, guys. Well, thanks everyone for your time. Don, excellent as always. We'll be posting this to our webinar page and our YouTube page as soon as I can edit it. So, yeah, thanks again, and look out for the next webinar when we send out the email. Appreciate your time, everyone.
Thanks, guys. Whoop, my hand's invisible. There it is.
Take care.
Bye-bye.